Anybody out there?
I got the camera in.
Apparently, either that or you're real fast with crayons. So now everybody has a camera. That's wonderful.
Pretty sure you don't want to watch me eating lunch, so I'm going to go ahead and kill the feed.
Oh, actually, I was looking at that chair behind you. Looks comfortable.
Yeah.
Anybody want to guess where that picture was taken?
Canada?
Yep. Yeah, that's at the Toronto airport, actually. Well, by my watch, it is noon, so it is time to get started. I'm going to place a practice exam on, I'll make it available to you. I'm not exactly sure how to do that. I just wrote a real quick, like a quiz, but my goal is to hook it up so that you have to use that lockdown browser and Respondus so that you can check and make sure that your hardware all works and you have all of the required software. Unfortunately, I have not yet deciphered how to do that. So that I'm working on that. And as soon as I get it figured out, I'll let you know. Guess I should start the timer. Everybody here? Any questions? No, as promised.
Not yet.
Not yet what?
No questions
not
yet, is what I meant.
Oh,
Yeah.
oh. I thought you were saying, don't move on yet.
Oh, no.
You get red. You made me see red. Okay.
Uh-oh.
Last, what?
Sorry, when was the exam?
Last, it's going to be a week from today.
Gotcha.
And there'll be a practice exam sometime before then. Actually, the practice exam has to take place before our meeting on Monday so that I can ask whether anybody had any problems with it. So watch for that.
Will that practice exam be a review of this material or just to check to see if the hardware works?
You know, I'd like it to be a review of the material, but I'm more concerned about getting the hardware working. So I'm not going to promise anything. But that would sure be a nice idea, wouldn't it?
Good night.
Okay.
Somebody needs to mute their mic. Okay, we're going to talk some more about some peripherals with a pen that doesn't seem to want to work. The next peripheral that I want to talk about is the keyboard. And now, the thing about the keyboard is there's a lot of stuff. In truth, that one little key right there, that should be accessible to the CPU individually. And typically there's 101 keys on a keyboard. And the CPU just does not have the time to check with each one of those keys and see whether it's being pressed. Now, we've talked about this before. The solution to that was, what's the solution to not having to check all these things? See whether the key's being pressed?
Using an
An
interrupt.
interrupt controller.
Interrupts, that's right. Interrupts are the solution. Rather than the CPU going out and asking who wants its attention, whoever wants its attention makes it known. Well, the keyboard does the same thing. There are really only 4 wires from the keyboard to the CPU. So obviously there's not a wire for each key or anything like that. Actually, the keyboard, from the very earliest times of the IBM PC, the keyboard has its own CPU. And it's a little tiny CPU. It's not very powerful, but its job is to continuously scan these keys. And when it finds that a key has changed, it puts together a package of information and sends it to the CPU. Now, notice I said whenever the position of a key has changed. I didn't say when you press a key, although that certainly works. When you press a key, this CPU notices it, and it takes a code for that key called a scan code, Now, you don't need to know what the scan codes are. I don't think any human, well, some humans know, but it's not important. It's a code that tells the CPU the position on the keyboard of the key that was just pressed. It does not imply anything about what character that key represents. And that's very important. The translation from position on the keyboard to character is done by the keyboard driver, the device driver for the keyboard. And that means if you want to change from an English keyboard to a Czechoslovakian keyboard, all you need is the keyboard and a new driver. And that's really all there is to it. So the CPU notices a key has been pressed. It takes the scan code for that, which is, it's a 16-bit value. So it takes the scan code and it sends it to the CPU. And then it also sends the CPU the status of the keys that modify things. So you look on your keyboard and you see that there's a shift key and there's a control key and there's an alt key, et cetera, et cetera, et cetera. And the key that just got pressed, its meaning may be changed by the fact that the alt key is being held down or something like that. So every time you press a key, the CPU is told which key was pressed in terms of its position on the keyboard and the status of all of the modification keys. Now, it really gets into detail because the left control and the right control have different scan codes. They're different keys. And so the package that gets sent to the CPU has to include the right shift and the left shift, and the right control and left control, and the right alt and the left alt, and anything else that needs to be done. And so that's how the keyboard notifies the CPU that a key has been pressed. And then when you release the key, exactly the same thing happens. So the CPU sends another scan code, only this is a key up code as opposed to a key down code. So the CPU can time how long you've had that key pressed. That's one thing it could do. It could, let's say sometimes when you hold the key down in a word processor, it just starts repeating that key. Well, that's how it's done, is the CPU gets a key down code and it starts a timer. And when that timer runs out, if it hasn't gotten a key up code from that same key, then it just starts auto repeating. So that's all done by the driver. That's not done by the keyboard. There's also a right shift, not a right shift, a right space and a left space bar. Some keyboards do have the space bar split. And so there's two different codes for that. So keyboards are pretty simple. That's all there is to it. It's just this little CPU in there. Every time a key changes position, if it goes up or down, it doesn't matter, the CPU gets a code. So I press this key, I get a key down code sent to the CPU. Now, if I hold this down and I press this key, I'll get a key down sent to the CPU for this guy. And then whichever one I let up first, get a key up code to the CPU, and then you let the other one up, you get a key up code to the CPU. You want to see your CPU go insane sometime? Set something like a coffee cup down that presses 3 or 4 keys and just leaves them pressed. When your word processor is running, you get a really interesting letter that way. What shudders a bit, stutters a bit, what does? I'm looking at the chat over here. Everybody having video latency issues? Is the video okay?
You're showing real bad latency issues from your primary camera there, boss. We can hear you just fine, but your video's lagging behind about 3 or 4 seconds.
So if I touch the CPU right now, you don't see it for 3 or 4 seconds?
Correct.
Huh. Well, I don't think there's much I can do about that. Let me know if it gets really bad. So any questions about a keyboard? Very simple device, but very necessary. Okay, well, we can move on. How about a video monitor? Well, we know that the CPU is not going to go out and individually write every one of the bytes to the screen. The screen is bitmapped. Well, first of all, and you probably all know this, but the screen is made up of pixel picture elements called pixels. And a pixel is a spot on the screen. If we blow it up, it's actually 3 spots, one for red, one for green, and one for blue. Red, green, and blue. So that's red, green, and blue. Now, in memory, in your video memory, there is a word which corresponds to this very first pixel, this very first pixel element up here. There is a word in memory that corresponds to that position. Now that word in memory has got to carry all of the information about that position. In the early days, that was pretty simple because the only thing that you could have there was an ASCII character. And so it was a 16-bit word that corresponded to that. And the first byte of that 16-bit word was the ASCII code. And the second byte were bits that indicated things like, should it be dimmed or bright? Should it be underlined or not underlined? Should it blink or not blink? I think that's all there was in the beginning. Well, in today's world, it's a whole lot more complicated. The pixel, since it's now color instead of black and white, we actually have to provide values for the red, the green, and the blue portions of the pixel. So that's usually done with 24 bits. Notice how 24 bits just happens to be 3 bytes. So 1 byte for red, 1 byte for blue, 1 byte for green. I guess this should be G and B. RGB is how it's usually referred to. So the red intensity of this pixel can vary between 0 and 255. The same for blue, the same for green. And so when you put it all together, you've got 2 to the 24th different colors. What is 2 to the 24th?
That's
2 to the 4th is what? 2 to the 4th is 16.
16. Oh, 16 MB. 16
Not-
megabytes.
Not MB. 16 mega
Megabytes.
colors. Mega
16
colors.
Okay, M.
See, there's
MC.
3 bytes. Yeah, okay, MC. There's 3 bytes per pixel. And so what we're figuring out is how many colors you can see. So 16 million colors. That's quite a lot of colors. That's a heck of a lot more than any human can discern. But that's the way it is. And then since it's a 32-bit system, we've got
30,
some bytes out here
2,
for things.
34, 36.
What? If you're going to mumble to yourself, turn your mic off. If you want to say something, then turn your mic on and say it. So, how many pixels are there? Well, that's the resolution of your screen. So if you have 1024 by 768, this used to be a very common resolution, and I use it because that's a very nice number to work with right there, that 1060 or 1024. We have 4 bytes per pixel. And how many pixels do we have? Well, we've got 768K, because that's a K. So it's real easy to figure out how many pixels there are. 768K pixels. Each one of them takes 4 bytes. And so that's what, 3.5 million, maybe? Nah, probably not that high. Whatever 3 times 768 is. It's going to be something like 25 million, maybe. But it's a lot of memory. It is a lot of memory. In the olden days, the memory for the monitor was part of the main memory for the computer. They carved it out of the main memory. So that's just less memory that is available to hold your program and your data and stuff. Now, modern computers, all of this memory is in your graphics card. And so the graphics processor, or processors, plural, they're just working their tail off, keeping the screen refreshed. So we've got to write, what did I say? What's 3 times that? 3 times 8 is 24. That's 20. And
That's 2304.
2304. Okay. Anyway, so let's just say it's approximately 2.3 megabytes. Now these really are bytes. 2.3 megabytes to represent the screen. And the computer has to update each one of those. How often? No, that's your refresh rate.
The refresh rate on my monitor is 1 millisecond.
1 millisecond. So it updates
144 hertz.
1,000 times a second. You're sure about that?
I believe so. If I have the proper
think so.
graphics GPU with it, it's a gaming monitor.
No.
No,
Well,
you're talking about
okay.
response time. 1 millisecond response time. It's probably 60
okay.
hertz or 144 hertz.
It's 144 hertz. Then.
Okay, so 144 times a second. And so if you multiply 2.3 times 144, you get, I don't know, 200, about 300 megabytes per second. So that's the bandwidth you have to that monitor. Now, if you've got a refresh rate of 144 hertz, everybody know what a hertz is? Okay. If you've got a refresh rate of 144 hertz, you probably are not running at this low resolution, because this is a pretty low resolution. Back in the days when this was considered normal resolution, 60 hertz was the normal refresh rate. You wanted to get fancy, you could go up to 72 hertz. I don't believe that most people can tell the difference between 72 hertz and 100 hertz in refresh rate. I just don't think your eyes work that well. And this is way overkill for people.
Between 60 hertz and 120.
I'm sorry, what?
I said, I can tell you for a fact, there's a noticeable difference between 60 hertz and 120.
Yeah, you must have better eyes than I do then. I've read some studies. There have been a lot of studies done on how many different colors can a human discern. You know, do we need 16 million colors? And the answer basically is no if you're talking to people. But if you're talking about people, but if you want to project your image up on the wall, then you do need a fairly high resolution, because the bigger that picture gets on the wall, the further apart your pixels get. So you would like to have more pixels so that you get a better image. Now, the way, so everybody's got flat screens these days. So it just starts up here in the corner and it writes the data in, and whatever it writes into memory is what you see. You can also do screen buffering, which means that you set up two areas of memory that are going to represent your screen. You fill one of them and you display it on the monitor. And then while that one's being displayed, you build a second image in another area of memory. And when you want to change to that second image, you don't have to write all of these pixels to change. All you have to do is change the base point of what's being displayed. And you're now talking about a new video image over here. And it just takes lots and lots of memory. I've got, I think my graphics processor has 4 gigabytes of memory in it. So that, you know, I'm running 3 screens at fairly high resolution and it works just fine. The graphics processor is capable of taking over the address, data, and control buses and moving information from its memory into the main memory, or for that matter, onto disk. It can be a bus master. Any device which has the, I guess, permission and ability to take over the buses and communicate with other devices that are on those buses, that's called a bus master. So the graphics controller can be a bus master. It can talk directly to the memory controller. It could talk directly to the disk controller, and any other controllers you got laying around. So that's how memory, that's how image information moves around so quickly, is it just bypasses the CPU. In fact, the processors in the graphics control card are to some extent more powerful than the CPU. Now, they're not very general purpose. Graphics processors are very, very specialized, but man, they do what they do really, really well. And if we have time toward the end of the semester, I've got a 1 lecture presentation about the graphics processor, so you can see what it does. Any questions about a monitor? Okay. Anybody have a favorite piece of hardware that they would like to know how it works? No?
No.
Okay. Well,
Yeah. USB splitters. I really find them useful to take one USB port, go to 6.
okay. Well, there's various ways of doing that. USB, Universal Serial Bus. It's actually, it's sort of based on what was called RS-232C, if you want to be really, really particular about it. This is funny. This has been the standard for serial communication, just varying in speed, basically, for decades. But that R right there, That stands for recommended. This is a recommended standard. It was never completely and formally adopted, but it's the standard. So USB, okay, so this is a two-wire system. RS-232 is a two-wire system for the data. Now, it was really designed so that a computer could hook to a modem, and then the modem converted the data into tones, which were sent over the phone line, dial-up. I don't know whether any of you have used dial-up, but that's what it was. In today's world, if you want to send something over the internet, you still send it to a modem, but it converts your data into electrical pulses out on the internet, or the Ethernet, or whatever kind of net. In my case, it's Comcast cable. But it all kind of goes back to RS-232. The nice thing about USB is that it's plug and play. With RS-232, you pretty much had to have the device plugged in at the time you booted your computer, otherwise it wouldn't be found. With USB, you have a USB controller. USB controller. Also called a hub. And it's got 4 wires that go out. 2 of those are power. Now, this is a plus and minus. It was 5 volts. This was an addition. RS-232 didn't have any way of powering the remote device. But back in those days, remote devices used so much power that you probably wouldn't want to do it over a long distance anyway. USB controller supply. Now, this would be a powered hub, which all computers have. And these are the data lines. Okay, it's two-way. So one of them is transmit, and one of them is receive. And it uses the negative side of the power for common. So here's your common, here's +5, here's transmit, here's receive, and it's all with respect to this, which eventually someplace goes to ground. When you transmit something out here, it's got, well, let me first say, when you plug in a USB device, let's say that USB device gets its power from here. So it's like a mouse. You plug it in, gets its power. When it powers up, the first thing it does is it sends a packet out that says, I just powered up and I am a mouse. And the USB controller looks to see whether or not there is a device driver for that mouse that just got plugged in. And interestingly enough, the device driver is particular to the port where you plug the mouse in. The first time you plug it in, the controller has to go find the device driver and install it, and then eventually your mouse starts to work. Now, if you unplug that mouse and move it to a different USB port, the USB controller is going to go out and find a driver for a mouse on that port, which I think is interesting. You can have multiple devices hooked up to this USB controller. I think 32. To tell you the truth, I've never run into a problem where I had too many. Each one of those devices has an address, and that address is determined at the time you plug the device in, and it says, here I am. The USB controller installs the device driver and sends something back that says, okay, you're ready to go, and by the way, you are so-and-so. And from then on, it communicates. And then if you've got several devices plugged into this controller, they are differentiated from one another by their ID number, their device number. But that device number can change as things get plugged in and unplugged, the next time you boot, your mouse does not necessarily have the same ID, but you don't ever need to know what the ID is. So now, if you need a USB splitter, that's not really too difficult to do. The data portion here is what gets split, and the splitter just takes this information and makes it available out on different ports. Now there are two kinds. There are powered and unpowered. The unpowered kind just take this +5 and also move it out, which means that the sum total of all of the devices using this power is limited. USB 1, this was 0.5 amp, 500 milliamps. And now I think it's up to 2.5 amps per USB controller. A better way to split it, though, is to use a powered splitter, which then requires a wall transformer to supply extra power. So it's like a booster. So that's the simplest way to do it, and that's using a hub. I hope that answered your question.
Thank you.
Question, sir.
What?
Can you talk a little bit about the difference in RS standards, like 232 versus 485 versus 422?
Well, I'll not in much detail. I won't, because it just takes too long. There are so many standards. We'll talk about some of them. We can talk about RS 232, which is the basis pretty much for everything. So RS 232 C is asynchronous word, synchronous bit. Now, what does that mean? Well, it means that the receiver never knows when the next word is coming. That's asynchronous. It just happens whenever the transmitter wants it to happen. And the receiver has to always be ready. But once a word starts, the bits of that word come at very specific times. So that's why it's synchronous bit, but asynchronous word. One of the things about RS-232 and really any of these things, it's a protocol. Protocol is a set of rules. You hear the word protocol used in terms of diplomacy. It's a set of rules, okay? You don't, slap your host in the face and spit on the table and stuff like that. That's the protocol. In diplomatic, though, they usually talk about how many guns salute and how many people are there to meet them and all that kind of stuff. Well, in our world, protocol means a set of rules so that a sender and a receiver can communicate with one another. And in RS-232, the protocol, well, I'll talk about the protocol in a minute. Let's just look at the wire, okay? The wire has got two states. One is called marking, and the other is called spacing. This is the active down here. This is the 1, this is the 0. Now, in terms of voltages, it really, there's a lot of different kinds, but the original RS-232, the spacing, where can I write this? Spacing was anywhere from -3 up to -12. And marking was anything from +3 to plus 12. Notice there's a dead band in there from +3 to -3 that is not either one of them. So it was a split. You had to have negative voltages and positive voltages. Now, one of the things about USB is they've gotten away from all of this, and everything's on the positive side. So if we look at a transmission, this is the idle voltage up here. And let's just say that it's been idle, you know, since Lincoln was assassinated, a long time. And the receiver is just watching it. Now, this falling edge right here tells the receiver the word is arriving. And this time period right here, it's called a bit time. That's one of the things that the sender and the receiver have to agree on, is what is that bit time? And the bit time is called the baud rate. Now, the baud rate is how many symbols per second you can send. And in this case, a symbol is just a 1 or a 0. So the baud rate is equal to the bit rate. Now, in other forms of communication where you use quadrature encoding and stuff like that, the baud rate is not going to be equal to the bit rate. But in our case, it is. So we often take baud rate and bit rate and interchange them. Technically, you're not supposed to do that. So this first bit time here is called the start bit. The start bit. Wish I could spell. Now, the start bit doesn't carry any information. It's just to allow the falling edge and then to allow the receiver some time to get ready. So after the start bit comes the data. And the data comes in bit times. These are the periods of time. They're equal to that right there. So here's 7, 6, 5, 4, 3, 2, 1, 0. So there's 8 bits of a byte. Remember, we agreed on this period of time. That's the baud rate. Originally, this was all originally designed for teletypes. Teletypes are those machines that sit in the back of the newsroom and that you hear them on the radio, and they and a teletype used RS-232, but it didn't use voltage as the sense. It used current. It was a 75 milliamp current loop. When no current was flowing, it was let's see, when no current was flowing, it was marking, and when current was flowing, it was spacing. And so you can get really, really long distance communication this way, because all you have to do is just crank the voltage up till you get 75 milliamps. Of course, that means, you know, there's 3,000 volts on this telephone line that you're sending it over, but it's technically possible. So for long distance communication, current loop is the best way to go, because the current is the same everywhere in the loop. If you're looking at voltage, the further away from the voltage source you are, the less the voltage is going to be, because you got voltage drop across the wire. Anyway, we've got this data. How many data bits are there? Well, believe it or not, that's something that you have to agree on, the number of data bits. And that could be well, let's see, baud rate could be anywhere from 75 up to, oh shoot, 119,000, something like that. And maybe even faster. That's just when I quit paying attention. Data bits are basically anywhere from 5 to 8. So you have to agree on how many data bits there are. So that means we know how many bits to expect, and we know how often they occur. Now, we're going to sample the signal in the middle of each one of these bit times. So how do you sample the signal in the middle of one of those? Well, the receiver, when this thing drops, when you get the start bit, it starts a clock called the baud clock. And the baud clock runs at 24 times the bit rate. So from here to here, the baud clock is going to go up and down 24 times. And so we count those. And when we get to number 12, that's when we sample. Of course, we don't sample anything in the start bit. So this thing falls, we wait 24 plus 12, 36, sample. Wait 24, sample. Wait 24, sample. Wait 24, sample, et cetera, et cetera, et cetera. So that's how we get into the middle of the baud. Now the transmitter, the sender, also has a baud clock going. And in the middle of each one of these is when, well, no, that's not true. The sender changes them at the beginning of the baud window. The receiver samples them in the middle of the window. Now, what would happen if the receiver's baud clock was off a little bit from the sender's baud clock? Well, what would happen, effectively, what would happen is the point in time where the receiver samples the data would tend to shift inside this bit window, and it would mosey toward here over time. So this bit might be right, but this one might have shifted a little bit. And it's an exercise that we used to have students do. Given a percentage of error in the baud clock, how many bits consecutively can safely be sent before you aren't synchronized anymore? But we're not going to do that. So anyway, we got a number of bits. They get sampled at each of these times. And then part of the protocol is parity. Now, there were lots of choices for parity. In my opinion, some of them were pretty stupid. Obviously, we've got no parity. That was a choice. If you're going to have parity, what kind of parity? Well, we know about even parity. We know about odd parity. Those are the two useful parities. They also offered choices for always a 1, always a 0, which that's what I think is stupid. If it's always going to be something, then you don't need to have it. Anyway, if parity is going to be part of this communications protocol, then the parity bit occurs right after the data. And then finally, we have a stop bit. However, it's not quite that simple, because part of the protocol is the number of stop bits. And this could be 1, 1.5, or 2. Those are the three choices for the number of stop bits. And so this stop bit is going to be however long you've chosen. And at the end of the stop bit, the signal is made spacing again, and it's ready to transmit another word. So when this thing drops is asynchronous. After you've sent this word, a week could go by before you send another word. That's the asynchronous word part. But once the word starts, everything is synchronized to that baud clock. So let's see, a standard, what most people would do would, it's not exactly right, but we kind of said, okay, for every character we're going to send, for every ASCII character we're going to send, it's going to take one of these per ASCII character. And we figured there's about 10 bits in here. So we say that if your baud rate is 300, you can send 30 characters a second. If your baud rate's 75, you can send 7.5 characters a second. Back in the old days, when you actually had dial-up modems and whatnot, if you were running at 300 baud, you could actually watch the characters appear on your screen individually, like somebody was typing, a slow typist was typing them, or even a fast typist for that matter. Technology got better, and 1200 baud became a really common standard. And at 1200 baud, it was coming out really faster than you could keep track of it. It wasn't just boom and there's a whole screen full of data. You could obviously see it filling up, but it was coming out faster than you could read it. But today we're talking baud rates in the millions, and that's USB baud rates. So this is how RS-232 worked, and it still works. If you have a connector on the back of your machine that looks like this and has 9 pins, that is RS-232. It's called a serial port. It's really old style. Not many computers still have them, but my motherboard doesn't have a 9-pin sub-D on it. I had to actually buy a daughter card and plug it into my I/O bus to get this. And I needed this because I have an UPS power supply, an old one that has this kind of communication, and it communicates with the computer. And if there's a power failure, it'll tell the computer to shut down and all that kind of stuff. So I've got one, but they're not very common.
I don't think they're common on personal computers anymore, but I've seen them on implements in industry still being used to this day. I can think of 3 examples off the top of my head where I have RS-232 interfaces at work that we have to work with.
Now, you may ask, why are there 9 pins if it only takes 2 bits to send the information? And you're absolutely right. It's not necessary to have 9 pins. But remember, this was originally designed to interface with a modem. And the original RS-232 standard, recommended standard, included signals for housekeeping. So there was a signal that went from the modem back to the computer saying, I'm on. And there was a signal from the computer to the modem saying, I'm on. And a whole bunch of these things. In fact, the original RS-232 standard called for a 25-pin connector. But when IBM designed their personal computer, for some bizarre reason, they hijacked the 25-pin D connector and used it for printer. And they took and they made the serial port this guy. I don't know why they did that, but they did, because there was a perfectly good printer port standard already in existence, the Centronics. But IBM never did like doing things the way other people did it. Any other questions? Okay, My turn to choose. Optical drive. This would be a CD, a DVD, a Blu-ray. What else is there? Yeah, that's pretty much it for now.
Disc. Disc.
What?
Laser disc.
Yeah, I don't know anything about laser discs, to be honest with you.
It's a dead format. They were CDs that were about the size of 33s.
Well, I know what they are. There's a guy lived across the street from me that was an audiophile. And this was back when 4-channel stereo was popular. And you had to spend thousands of dollars on a 4-channel FM receiver and a 4-channel Blu-ray or disc player and all of that. So yeah, I've seen them, but I don't know how the information was recorded on them. So I'm not going to talk about them. I know how this information is recorded. So we have this big disc made of, it's got waves in it like that on the side too. Hole in the middle so that you can rotate it. In a lot of ways, it's kind of like a hard drive. The information is stored in a track, but unlike a hard drive, this track spirals in. There's only one track. And remember also that originally this format was designed for music. So a lot of the specifications have to do with time. For instance, a CD, original CDs, I think were 74 minutes. Even when they were being sold as data CDs, they'd say 74 minutes. Because that's how they originally thought of them. So the surface of the platter, looking at it from the edge, there are these pits that can be drilled into the surface of the plastic. It's just a plastic platter. And it's drilled in with, well, the original is done with a laser, a high-powered laser. But then these things are manufactured. So what they do is they make an aluminum mold, which would have a protrusion right there, so that when they use this mold to make this piece of plastic, there'd be an indentation in the plastic. So they use these metal molds and they just stamp these things out by the billions. But the hole or lack of hole is what gives you your ones and zeros. When this is played, there is a laser that shines a light down there, and the laser detects whether there's a hole or not. Okay, how the heck does the laser detect whether there's a hole or not? Well, this is kind of cool. The surface of the platter is shiny. So it reflects the laser light very, very well. The bottom of this hole is also shiny. I think what they do is they mold the disc first, and then they deposit the shiny layer. That's how it gets down into the hole. Okay. Now, my printer is making weird noises. Here comes the laser light. Okay, so the laser light comes screaming through here. Now, if the laser light hits where there is no hole and it bounces back up, there's a detector in here too. The electronics can measure how long it took for that light to get down and come back up. So obviously, when it's over a hole, the light is going to take longer to get there and to come back up. But they go even further than that. These holes are exactly lambda over 2. That's lambda. What does lambda mean? You guys are sophomores, so you may not know this, but lambda is the common abbreviation for the wavelength of this light. So, you know, light from the peak of one to the peak of the next, that's the wavelength. How far does the light travel in that distance? And how close? And that is a function of the frequency of the light. Now, what happens, since this is exactly, I'm sorry, I told you wrong. It's lambda over 4. It's a quarter wavelength deep. Quarter wavelength deep. That means the light has to travel an extra quarter of a wavelength before it gets to the bottom, and then it has to travel an extra quarter of a wavelength before it gets back up to the top of the hole, in comparison to this light. This light travels half a wavelength further. That puts it exactly 180 degrees out of phase with the original light. And so the electronics doesn't even have to time this stuff. All it has to do is take the return and compare it. You take the phase of the return light and compare it to the phase of the transmitted light. If they're the same, then there's no hole. If they're out of phase, there's a hole. And so we can figure out whether it's a 1 or a 0. That's pretty clever. It takes minimum electronics to figure all of this out. Now, if we look at a track, this track, a section of it blown up, it's not really a continuous line. It's a series of holes. They're not called holes, by the way. They're called pits. And where there is no pit is called a land. So we have pits and lands. That's the 1 and the 0 in this world. So a track is really just a string of holes and no holes. And as this disc spins, the head has to keep right over that track. But the track's not always in the same place because it spirals in. So the head has to be able to track the track. How does it do it? Well, it does it by, they actually have a series of holes that are at very specific intervals here on each side. And by looking at the return, there's a tracking laser. This is the data read laser, but there's also a tracking laser. And by looking at the return from these pits, it can tell whether it has drifted to the right or to the left, and it can correct. The way it actually does that is it gets a right signal and it gets a left signal, and it combines those, and when it's perfectly over that, the combined signal should be 0. If it's positive, that means move the head in one direction. If it's negative, that means move it in the other direction. So it can track this. Now, how does it, if there's a land, you know, if there's a pit, oh, Great. Just hit the camera. I have this is taped down so it doesn't move anymore. I need to nail the camera down, apparently. Okay. Can everybody see that?
Yeah.
There we go. Okay. If there's a hole, a pit, then it's pretty obvious that there's a piece of data there. But if there's a land, meaning no hole, you've always got this nagging suspicion in the back of your mind. How do I know whether there is a data bit there? Since there's nothing there, it looks just exactly. The only thing that's different between right here and where the data bit is where it is. There's no visual reference at all. The bits are read by virtue of the speed of the drive. So it's all timed. Now, if you remember, in the hard drive, the platter rotated at a constant velocity, constant RPM. That was called constant angular velocity. In other words, the angle that is swept in a certain amount of time is always the same on a hard drive. Constant angular velocity. Now, a CD, on the other hand, an optical drive, is constant linear velocity. Constant linear velocity. That means that the rate at which the bits, the lands and pits, the rate at which they travel under the laser is constant. Now, that means that out here, the disk is going to run slowly, and in here, the disk is going to run quickly. As it moves, it is constantly adjusting the speed of the disk to get the right speed. And the right speed is when the electronics is expecting the bits and they're there. That's the right speed. So there's a big difference between optical and hard drives. Optical drives are constant linear velocity, and hard drives are constant angular velocity. This is all described, by the way, in something called the Red Book. That's not a women's magazine that you pick up at the grocery store. It's, well, it started off as a folder, a 3-ring binder that was red. And that's where they kept the standards as they were developing them. And then they had to modify that standard so that data, not just music, but data could be stored on here. And so when they did that, they changed the color of the binder. And so they refer to all of these standards for optical drives by the color of their book. So you've got the yellow book and the red book and the blue book and just blah, blah, blah. And it's very boring reading. In a CD, the data is stored in what's called PWM, pulse width modulation. Pulse width modulation. That's just a fancy way of saying that. Let's look at an audio signal. Here's an audio signal that you might see on an oscilloscope. And what we do to digitize this is we take readings of the voltage every so often. It's almost time to go, isn't it? You guys need to take a test, a quiz. I forgot about that. Okay, real quick, go take the quiz on Canvas. Quiz, what is it, 5?
Oh,
I thought we did 4 last time. I don't know, whichever one's at the top of the list. My problem is that I think the last time I tried to go to Canvas, I closed Zoom somehow. So I don't want to do that again.
I think your video latency's gone.
So I could dance and you'd get the whole,
So what's stopping you?
oh, that's a cat.
Yeah. Cat fur.
Okay, is everybody done? All right. So move on here in the last few minutes. All right, so what I was saying is if this is an audio sample, we digitize it by measuring the voltage here, measuring the voltage here, here, here. You just measure the voltage every so often. And that every so often, excuse me, is the sampling rate. In PWM, these sample values are just stored. That's all there is to it. PWM signal would look something like, after it's been digitized and we're going to write it to a file or something like that, it would look like right sample 0 followed by left, this is assuming it's stereo, of course, left sample 0, and then right sample 1, left sample 1, right sample 2, left sample 2, et cetera, till you run out of data. This PWM standard allows for any number of tracks. That's something that has to be known. There's usually a header on the file that says how many tracks there were and what the sample rate is and all that kind of good stuff. But on a CD, there is no encoding at all. Those are just straight voltage values. And you could easily write a C program to read a WAV file, which is a PWM file. And that's the way stuff was stored on CD. It was very, what should I say, straightforward. It was brute force. And that, of course, is no longer how things work. Nowadays, you compress everything, especially when you got to video. You could not do this for video. I mean, the file size would just be outrageously large, probably terabytes of data for any kind of video that you were storing just as voltage values, because you'd have to be storing a green value and a red value and a blue value. And then, of course, you also have to be storing the audio, but it turns out that the audio represents such a tiny little fraction of the data that you can basically ignore it. You can get by with audio, well, CD audio, I can tell you, CD audio was sampled at 44,100 samples per second. If you were to sample video at that rate, it would be very, very choppy. So DVDs, Blu-rays, those are all encoded. Yeah, that's what we mean when we say MPEG-4. Those kinds of terms are how the data has been compressed. I ran some tests, and that video I did of the first lecture, the one I had to compress because it was too big, it was 20.56 gigabytes using Ultra HD. And these are the specs on Ultra HD. But here's what I want to show you. When I took that same video and I used this compression method, it got down to 59 megabytes. That's 350 times smaller. Of course, it looks like crap. But you know, it's smaller, and depending on what you want to do, it may be good enough. You don't need super high resolution if you're going to look at something on your phone, because you just don't have the resolution. So time's up. We will continue this discussion on Monday. There is homework due on Monday, don't forget that. And then there's an exam on Wednesday. Look for the practice exam somewhere in the near future, coming to a screen near you. So everybody take it easy, and we'll see you next time.
Excuse me, Professor.
Yeah.
I got a question. So on the quiz that I just took right now, it's not counting the correct number of correct answers I got. I was wondering if, like, maybe you can take a look for me, because it's not counting the 2 out of, for example, the question 2, I got 2 out of 4 correct, but it's not counting those two.
I think it's subtracting any answers that you entered that were wrong.
I see.
Yeah, because I
So-
noticed the same for me.
Yeah.
So,
okay, I got you.
Well, that means you could get minus scores.
Yeah, I did the same thing to me.
Yeah.
If you answered every single question 100% wrong, you're telling me you'd get a minus 12?
Yes.
Potentially.
Yeah.
Really? I have never
Yeah.
seen a negative number. Huh.
Well, I didn't get a negative
It-
number, but
I
you
mean,
know,
it would probably end up throwing you at a 0, but
yeah.
yeah.
Well,
I think you can only get a minus 10.
but that no, there's 12 points on this one. That guy,
There's 12 points, but there's only 10 wrong answers.
no, there's 12 points because there's 12 right answers. Oh, there's only 10 wrong answers.
Right. So you could get a
It's-
minus 10
Oh,
up to a positive 12.
I'm gonna test that and see. I never did test it. When I test these things, of course, I put the right answers in. So you get +1 for a right answer, and you get -1 for a wrong answer.
Yes.
Yeah.
Wow. I did not realize that. Well, any other questions? I guess I set it up so you can see the right answers now?
Yeah.
Yeah.
Okay. So you're all happy?
Yeah, I appreciate it. Thank you.
Okay. Can I go away now?
Yep.
I was going to ask real quick if we're not going to get any test objectives or review or anything.
Well, I don't typically. Usually what I say is homework, quizzes, and previous exams. That's your best study guide right there. If you can do every problem that was on the first exam, even changing the numbers, you know, and you can do all the homework problems and you can do all the problems on the quiz, you're not going to have any trouble with the exam.
Okay. Thank you.
Because I'm not going to throw anything new at you. I'm just going to take stuff you already know and twist it a little bit. All right. Bye.
Bye.
Right.